Have you ever created data structures and put your data into those and actually thought about how much memory do those take inside your application? Have you thought what will happen if you multiply that tiny little set or a list or whatever you created by hundreds, thousands, or millions, and how much memory that will take and how much memory savings you can have? Well, this talk is about all that. This talk will be talking about performance and scale in Java and how you can handle both domain-oriented objects and tabular data structures in JVM in Java in general. Before we go any further, I think it's a good idea to introduce ourselves. So, Donald, you get to start.
Thanks, Rustam. So a little bit about myself. So my name is Donald Raab. I'm a managing director and distinguished engineer at Bank of New York Mellon. I am the creator, project lead, and committer for the Eclipse Collections project, which is managed at the Eclipse Foundation. I'm a Java champion. I was a member of the JSR 335 expert group that got lambdas and streams into Java 8. And I am a contributing author to the 97 things every Java programmer should know. So.
And my name is Rustam. I am a chief engineer at a company in Norway, Oslo, called Compitas. I'm a Java champion as well. I'm also a Google Developer Expert for Cloud, and I am a Java 1 rockstar, and I also have been involved throughout times in different communities, and I'm leading one of those at the moment as well. So, enough about that. Let's talk about a little bit of history. So rewind a tiny little bit back and talk about what was happening in 2004 and why it's important.
Yeah, so back in 2004, to give some context, I was working in a financial services Java application and had a problem. It didn't fit into a 32-bit memory space. And my mission was to try and fit 6 gigabytes of stuff into a 4 gigabytes of space, right? Once I dug into looking at the problem, it turns out there were millions of small list set map instances roaming around that were created with default sized array. And at the time, the solution we came up with was to actually roll our own small size Java collections. And I felt a little bit, for those that know the movie The Martian, I felt a bit like Mark Watney, where he said, in the face of overwhelming odds, I'm left with only one option. I'm going to have to science the stuff out of this. So if you fast
what
forward
happened afterwards?
Yeah, so fast forward to, after 2004, when we, got 64-bit JVMs with the JDK 1.4 release, we could now access more memory on our hardware, but the, software problem, accessible memory, became a hardware problem, right? It's like you wind up with, over a period of time, how much memory do you actually have to access, right? And really, it's like we wound up, pushing hardware limits in some cases with some of our heap sizes. So compressed oops gave us a great benefit when that became available, JDK 1.6 in 2006. We then got the ability to have 32-bit references instead of 64-bit references in our heap. Saved a significant amount, but there was this then problem where it's like we got back to a software problem again. It's like now we have this sweet spot for the 32-bit references. We got to keep it below 32 gigs, or there's this ability to play around with different shifting options where you could maybe get 32-bit references up to 64-bit gig, but you'll get a different alignment. So it might cost you 16-byte, alignment versus 8-byte. So you got to be careful with that. But 32 gig winds up being the sweet spot. So because of this, we wound up, then rolling our own solutions for our own mutable sets, maps, and lists, and also built eventually our own primitive collections. The whole goal being that we wanted to reduce the total memory footprint of our data structures and make sure our data was taking the most space, not the data structures. So then we can talk about the problem today.
The problem today is I called it simulated problem today because we have actually created a little bit of that problem, because now you have 64-bit memories, it's a systems, you have a bunch of memory and you have everything is nice and shiny, right? But the problem is still there because you still need to process more and more data, and you would like to do it in a much more efficient and the most efficient way. So what we have now, what we've actually tried to create this problem is that we've thought of a data put into a CSV file that we would like to read in. And since we do quite a bit of conferences, both of us, we decided to go with conference data. So I'll show you the data and what it consists of on the next slide. But for now, we just want to say that we need to read in data, we need to process, we need to do something with that data, and we want to do it in the most efficient way. So how can we do that in Java? What kind of decisions we can make to make it more efficient? How we should think about our data? Should we think of it as a rows of data, columns of data? Which one is better? Who would, we'll see. If you don't know, you'll figure out. So, and if you do, well, we'll see if we ended up with the same conclusions. And also what libraries that we'll be looking at. So we'll be looking at 3 different ways of doing stuff. We'll be looking at the batteries included version of Java. So Java collections that Java comes with. We'll also be looking into Eclipse collections, a library that Donald started, and there's a bunch of people have been contributing and creating, evolving. And also we'll be talking a little bit about, or quite a bit actually, about a library that was built on top of Eclipse collections, created by another developer, Vlad, called DataFrame EC. So if you can imagine, EC is actually standing for Eclipse collections. So this talk will be focusing on memory and memory efficiency and the strategies and techniques connected to that. We'll not be talking about other kind of performance tuning and all those things, but we can always talk about that in another talk, or after the talk, or offline, or whatever that might be. So let's talk about data. The data, the way it looks, it's a bunch of columns, like typically what you would expect from your data. It has an event name. It has a country where that event exists or will take place. It has a city where it will take place. It has 2 sets of date objects, or dates, where we have a start date and end date. It also has some kind of indication of what session types does it have. So a list of elements. So it might be lightning talks, regular talks, or workshops. And we have some integer values, or typically values that would be represented by integers, number of tracks, or number of sessions, or maybe even number of speakers, or cost, so how much that would cost. To create all that, we have a script or a Java class that randomly generates data, and then we can create and generate that in a kind of deterministic way, where we can just randomly generate a number of random strings going as names between a certain length of a string. So it can be a little bit smaller, a little bit bigger, but roughly the same size, and randomly generated. Same goes with the countries. We have a set of countries that we pull from, and we're gonna use those countries. Same goes with the cities. We also have dates. Dates are in our data set just for our testing purposes. We kind of limited that to be all possible dates within 2023. And also session types, and you can choose between those 3 that you can see there. It can be different variations of those and different number of those. And also, the other numbers are going to be kind of random within a certain range, right? We've generated it in different shapes and sizes. We generated it for like 1 million rows. That takes roughly 90 megs on disk. We have a 10 million one, which is 10 times bigger, so roughly 900 megs. And we also have a 25 million rows. Actually, we have 52, but that's a spoiler. So 25 million, which takes roughly 2.2 gigs on disk, right? So measuring memory costs. So how do we do that, Donald?
So real quick, and I guess this is a practical thing to walk away from this talk with, is there's a tool at the OpenJDK project called Java Object Layout, also referred to as JOL. So it's a great tool for analyzing the object layout schemes of various objects, and you can, it's very precise in terms of you can look at individual objects and look at their cost and layout. So you've got the Maven dependency here. You can go check that out. Also, like there's a nice article here from Bill Dung talking about memory layout of objects and actually talks about JAWL in more depth. There's also a Stack Overflow question, which I actually asked and answered, which was in regards to whether or not JAWL works with Java records. It does, and pretty much it requires using a VM flag when you're running with Java 14 or above. If you want to use records, you got to set this magic field offset to true. So we can talk a bit about what memory considerations we're going to look at.
And memory considerations, there are actually quite a few things, right? We would talk about boxed versus primitive. I'm going to just I'm just going to list them up and then leave the explanation of that as a kind of cliffhanger, or whatever taste for listening to the rest of the talk. So boxed versus primitive is a thing that we'll be thinking about, and we have been thinking about, and we'll be talking about. Also, we'll be talking quite a bit about data structures that are mutable versus immutable. We'll be talking about data pooling and what that actually means and what results it will give you. We'll also talk about the way of thinking of data. So do you want to think about it in a row-based way? So like you typically think about your data in a, I don't know, let's say relational databases and stuff, like row and row, another row and another row of data, versus column-based. So that's another thing. And we'll also be talking about how memory can be improved or will be improved in the future by the things that are planned to become a part of Java as well. So memory cost, boxed versus primitive. Take it away, Donald.
Yeah, so we're looking at two classes here, and there's some giveaways, but on the left you got the min-max primitives box, and you've got a set of fields which represent the min and max values of different types. And on the right you've got something that looks at very similar, different class name. All the field names are the same, and the primary difference is the type. On the left we've got the type with the uppercase letter, on the type on the right, the type with the lowercase letter. So question for you to think about real quickly is, what is the difference going to be between these two classes, specifically from a memory footprint perspective? So
the solution coming up, I mean, you can pause now. Solution is coming up in 3, 2, 1.
Okay, so what we're going to do is we're using JAWL here to basically print out the memory footprint of these two objects. And you can see we're using this thing called graph layout, parse instance. We give it an instance of min-max primitives boxed, and we print out its footprint to system out. And then we do the same thing with min-max primitives plain, print out its footprint. And what you see here is, so for the type that we had on the left that had the uppercase, type names like Boolean byte character all with uppercase, what you'll see is that we actually created in memory 17 different objects. And pretty much it was like the object that we wanted, the min-max primitives box, and then we wound up creating 2 objects for each of the min-max values of these box types. So in total, 17 objects, and for a total of 368 bytes of RAM for that single class. And what you can see is like in the middle, you see the average. You're seeing the cost of each of these box types. So it's just a useful metric for you to understand when you're using these box types in memory. What do they actually take in memory to use them, right? And in the min-max primitives box as well, you see it takes 80 bytes itself. That 80 bytes is counting up the 4-byte references plus the object header cost, right? So in addition to the cost of each of these objects, you've got the reference to the object as well contained in the main object. So 368. Now, if we look then at min-max primitives plain, you'll see we get 1 total object. So we basically get a savings total of like, we don't have to create 16 extra objects. We just have the primitive values. And the total cost of that object is less as well. It is 8 bytes less than the cost of the min-max primitives boxed, minus also then the 16 extra boxed wrappers that we get. So our recommendation here is pretty simple. Don't box primitive values, right? It's like, understand what the cost of doing that is. Now, unfortunately, because Java has auto boxing in it, that can be a useful feature, but it's also somewhat evil in that what it's doing is silently creating stuff on the heap for you, taking up memory, right? So using auto boxing, you may actually be hiding memory bloat. So now we're going to actually take a look at boxing different data structures, right? So boxed versus primitive data structures, as well as an alternate data structure in here as well. So here what we've got is we're creating 3 different sets. One is Java util hash set. We're going to then create a unified set from Eclipse collections using, and what it is basically, it's going to be a set of numbers from 1 to 10. So the first 2 are boxed, right? You can see they have hash set of integer and mutable set of integer. The third one's not boxed, it's primitive, right? So here we're going to basically compare 2 set implementations and then a primitive set implementation using JAL, doing the same thing, just parsing each one and doing their footprint. So what do you think the difference is going to be between these 3 classes, right? So
again, the answer is coming in 3, 2, 1. Ta-da!
Okay, so looking at hash set, what you'll see is like we wind up actually creating 24 objects here, right? Now 10 of the objects are the boxed integers, right? And they're taking 160 bytes. But we have the hash set itself, and then contained within a hash set is a hash map. And you'll see like within a hash map, you've got an array of this hash map dollar nodes, and you've got 10 of these hash map dollar nodes. And these are basically the map entry objects contained inside of the map. Now, the interesting thing is like, a set containing a map winds up, carrying along with it all this extra infrastructure to support its setness, right? If you then compare it to unified set from Eclipse collections, so Eclipse collections doesn't contain, the set for Eclipse collections doesn't contain a hash map. So you immediately cut the number of objects that you're creating in half, right? So we wind up with an array of object. We still have the 10 integer objects. We can't get rid of those because this is boxing happening. But then we've got the unified set cost itself, right? So big difference there, right? From 640 bytes down to 272, right? It's more than, cutting in half. Now, the third thing we can look at is the primitive set, so int hash set, right? And int hash set, what you can see is we get rid of the integer objects, so that's 160 bytes gone, right? We have an int array, which is that square bracket I, and then we have the cost of int hash set itself, which is 40 bytes. So in total, it's 120 bytes. So from unified set to the int hash set, you can see it's a tremendous savings, right? Once again, more than cutting it in half in terms of the memory. So
you kind of more than in half twice, right?
Yeah. And so recommendation here, avoid using Java util hash set unless you're using it in a place where you're going to create it and then get rid of it. Don't hold on to it long term because it's a lot of cost for the value it's providing of being a set. So it's a memory hog. Also remember, don't box primitive values if you can, right? Autoboxing's evil, right? You can see we get that 160 extra bytes for integer objects when they're just int values. They should be 4 bytes each, right? So it's hiding bloat in your heap potentially. So next thing we're going to look at, mutable versus immutable. So here we're going to compare 2 things. They're both in the JDK. We're going to compare hash set holding on to 2 integer values, 1 and 2. And we're going to compare it to the immutable set in the JDK. So if you use set.of, or in this case, we're going to create a copy of the hash set to save some code. So we do set copy of, and what this is going to do is create an immutable set for us, right? And then we're going to compare their 2 footprints. And if you look, here's the thing you just saw on the previous slide. You've got the footprint. Now this is only holding on to 2 integers now. Those cost then 32 bytes. But then you've got the cost of the data structure itself. So for hash set with 2 elements, you can see it's 272 bytes compared to this special type called set12, which is it's an inner class in immutable collections. And all you have is the 2 integers, 32 bytes, and then 24 bytes for the set12 for a total of 56 bytes, right? So a real tremendous savings, right, in the immutable range. So once again, avoid Java util hash set if you can. And recommendation here is like, if you can, like, when you're loading data up, if you can trim it at the end using immutable data structures, you can save a lot of memory that way. So I would say load mutable because it's going to be faster performance-wise to grow something that's mutable. But at the end, if you can trim and they'll wind up with just the memory required, going to an immutable version of the collection is very helpful. So then we can talk about sweating the small stuff. So we looked at like a set and a 2-element range. So it's like, well, what other optimizations can happen in that small element range? We're going to look at the immutable list space. And in the JDK, there winds up being 2 optimized immutable things. There's list 1, 2, which covers basically 1 element and 2 element. And then there's list n, which is basically going to be a trimmed array to the number of elements that you have. You can see, comparing JDK to Eclipse collections, This is what the differences look up to size 11, from size 0 to 11. And obviously, like, you're looking at memory in bytes, so the smaller the better. And you can see there's a reasonable gap between, at each level between JDK and Eclipse collections. Now, the reason is, like, Eclipse collections actually has named types from 0. So at 0, even though it looks like JDK, costs a lot more than Eclipse collections here, it's completely meaningless because empty winds up, there's only one in the JVM, right? You actually have a singleton instance of that. So you only ever create one. There's no multiple. Well, the multiple forward is 1. It'll never be more than that, right? Whereas the other ones, you're going to wind up with a multiple effect, depending on how many you have. If you have millions of them, that's where, like, savings can add up, right? So Eclipse collections actually has named types from, singleton all the way to decapleton and everything in between. And then at 11, it switches to the array base, which is where then JDK and Eclipse collections get very close, right, in terms of the cost, right? Now, there's a thing to be aware of in terms of, with this memory savings that you get, there is potentially a trade-off of performance, right? So the core JDK team made sure that they limited the number of classes they created to try and reduce the possibility of megamorphic call site sneak into your code. And when you have a call site that is bimorphic or monomorphic, it's very fast, right? And once you enter into the range of megamorphic, where you've got, let's say, 3 or more implementations of an interface, you wind up with a virtual lookup and method call, and that actually gives you a significant potential performance hit, right? So you got to be aware of, like, what's more important to you. Is it memory or is it performance, right? And I would say in that case, then making sure you understand your performance profile and where you have potential bottlenecks. Just be aware of the trade-offs, right? Where you recall in 2004, I had the problem of I needed to shave as much memory as I could to fit into 32-bit memory space, and that's where the design decision was kind of like driving having all of these smaller types available. So let's I guess go on and talk about exploring the 3 libraries we looked at.
Yes, so we kind of thought quite a bit about how should we present that to you, and we've mentioned already all of them, right? We talked about Java streams, talked about Eclipse collections, we talked about the data frame, but we thought of what is the best way of actually introducing them and actually explaining to them. So if you've used or played or seen Legos before, you kind of seen them in lots of different shapes and sizes and different things you can build them into things, but in general, you will see 3 different types of sets. So you will have the basic ones that are consisting on more generic pieces. That's a kind of Java streams, what it is. And also notice a little bit of as a fun, we actually looked at the age limits for those sets that we see on the picture here, and kind of is a fun comparison also for us as a programmers. So think of that as well, of I don't know, call it maturity or experience or whatever. But it doesn't really translate to that, obviously, but it's a little fun thing that made us kind of giggle a little bit. So Java Streams is basic building blocks. It has some quite a bit of assembly required to make it look like a car, but it's also a standard set of things that you can build into a house or an airplane or a boat or something, right? Most of the things anyway. But with Java Streams, it's the same assembly. Some assembly is required. More of a low-level control, so you can actually build your own stuff in a different ways. And also the Java Stream has this row-based approach to domain objects. So you have domain objects and you have kind of row-based approach to those, right? You put into an object a bunch of attributes and they kind of represent a row in a database. Eclipse collections is a little bit different, right? So it's more closer to what you see in Lego Technic, where you have all the pieces from the standard and basic stuff, but also has an extra pieces that are very specialized to build that particular thing. A particular set of cogs to do a transmission box for a car, or a tiny little thing to do the grill on a car, right? It's not the standard. You can't use it on many other things. But it's the same thing with the Eclipse collection. It has more specialized building blocks, but it's still compatible with the basic one. And it's also optimized for performance. So, it's optimized for building that particular car, obviously. And it still has the row-based approach to domain objects. You still put things into objects, and you still handle them as a bunch of attributes inside an object. Now, data frame EC is a little bit different. So it has a bit more of approach to similar to Lego Mindstorms, where it has a smart kind of thing in the middle there that can be programmed to do things. The way I like to think about data frame EC, which is probably not exactly the correct way, but it still helps me to build a mental model, is think of it as a spreadsheet, where you have both data but also smartness and filtering that you can build into a spreadsheet that you typically would have on your computer, whatever program you're using for that. So here it's like more specialized building blocks, even more specialized. They're still compatible with the two previous libraries or versions of doing things. It is much more higher level approach. But it also can be programmed in a more specific way to do specific tasks. It simplifies some of the tasks that can be done by the other ones, but are kind of a bit more tedious. And this one actually has a different kind of approach. It has a column-based approach to the tabular data structure. So now we're looking at data in columns instead of looking at in rows. So the Conference Explorer class that we had to implement to read all that data that we've shown you earlier, in most of the cases, at least 2 of the 3 cases that we've been playing around with for Java streams and Eclipse collections, remember, row-based approach. So that is a record that's implemented as a record where we have a bunch of attributes that we put into that. And then we create, for Java streams, we create a set of conferences and countries. For Eclipse corrections, we do a specific type of a set, which is immutable set, which is Eclipse collections, specific kind of object of, again, set conferences and countries. For data frame, you see things are a little bit different. So here we actually have a data frame objects for all of those things. So now we have a data frame for conferences, data frame for country codes, and all those kind of things. And you see it's not countries, it's actually country codes, because all the countries and everything, it's inside the conference's data frame. Country codes we need for other things to generate some other fun things. Let's don't get into that. But actually, one thing I should probably mention, if you want to know about APIs and all this, how it's been implemented, we've done a few talks earlier this year at DevNexus and DevOps Greece, where you can actually see the same data, see the same code, but where we talk more about using the APIs and how you can use it in different settings. So the question here is, what would it cost to load 1 million of conferences into data structures like this? Let's find out. First thing we would like to see is how it behaves when you do a type of a library and a type of data structure. So a type of library like Java or Eclipse collections or data frame, and for each of them, we'll kind of try to see for mutable and immutable data structures. And you can see the memory footprint of mutable structures are much, much, much bigger, at least for Java sets. It gets smaller
that
for
Java
the other
set
ones.
is exactly the set we kind of warned you
Yes.
about in the previous slides. That's Java util hash set, and you're seeing the extra cost there, how it translates as you scale up in terms of the number of
Exactly.
instances.
But still, I mean, even for the other ones, it's still higher, right? And this is for 1 million conferences. It's not for 25 or 50 or whatever. And also, the funny thing is that you can also see that the data frame EC1 is well, obviously doesn't have the mutable version, but immutable version of that is even half the size. And if you wonder why, that we'll see that in a little bit. So we're going to keep that and leave that as a question. So why are the collection alternatives comparing so badly to data frame EC? Well, we'll see about that. Well, kind of, this is the answer. I mean, not really kind of. It actually is one of the main answers. And the answer is something called pooling. If you haven't heard of pooling, we'll explain what it is in the next slide. So just bear with me for a little second while we go through and look at that. So now we've done the same thing. Library, immutable data structure, only immutable data structure, but now with or without pooling. And based on our data set, so this is the graph that you will not see exactly like this for your own data if your data is different from ours. But for us, it looked like that. And if we, with introducing pooling, we kind of halved or cut the size of the whole thing in two. Like I said, it's not the data structure. It's exactly the same data. It's exactly the same data structures. It's the only difference is if we do pooling or not. And we implemented custom pooling using Eclipse Collections for Eclipse Collections-based solutions. And the recommendation here that's important, if you're going to take away anything from this slide, is that you should understand your data and analyze it using some tools like Jol or something else to understand how it behaves and where you can optimize it. So, Donald, what is pooling? Can you explain a little bit about that?
First thing we got to talk about is what is a pool, right? So the way I would describe a pool is it's a set of unique values that you can put things into and get them out of, right? And if you think about a hash set in Java, right, you'll realize like the set interface does, you can add to it, but you can't actually get anything out of it. You can check for containment, right? So if a set had a get method, and there's actually a Stack Overflow question that someone asked and I actually answered, it turns out like in Eclipse Collections, our unified set is actually a set and a pool. So actually have a get method on our set, right? So what is a pool useful for? Why would you want to have a get method on a set? And what it's useful for is like, it helps you reduce the number of duplicate items that you have for a specific set of data in memory. So think of it basically as a hash map of the key and value being the same thing. I want to look up this key, and if I have that key, I want to look up this value, and I only want to keep this value in memory. But it's just with a set, since key and value are the same, a set, if you have a get method, you're looking up the key and you get back the key, right? Is really what it comes down to. So in JDK, there are different kind of pools that actually happen. They're not implemented as sets, but like there's a type of pooling, if you haven't heard of it before, which actually gets used for literal strings or string intern, right? So there is an internal pool that the JVM manages that literal strings use, and you can use it as well. It's a method on string to use a pooling. There are articles out that have existed for quite a long time, and done over the years explaining when and when not to use string intern and different issues with it. I won't go into that today, but it is available there. It is a pool. There are also these pools available on the boxed wrappers that actually get used through auto boxing. So there's a value of method on each of the boxed wrappers, like Boolean, short, integer, long, right? And there is a range kind of values that are basically cached or pooled for each of these types. So for integer, there's 256, I think, integers. So it's like negative 127 to 128 or negative 128 to 127. I forget the both ranges, but so they keep these small integers both in negative and positive cached, right? As it turns out, and this was actually a mystery for us at first, we didn't know why data frame EC was doing so well. Like we didn't do anything to it. We just loaded data into it. We thought we had a bug or something. Like why is it half the memory, right? And it turns out like data frame EC actually uses the Eclipse Collections unified set underneath to actually pool the data for each column. And it's very smart and makes sense because like for each column, since it's a column-based data store, it's going to say, well, if I have a string, let me have a pool of strings and I can unique while I'm loading. Or if I have a date, let me have a pool of dates. And even if I have like a tremendous number of years, the number of dates is probably going to be much less than, let's say, hundreds of thousands or millions, right? So,
well, but think about it, like 365 days, possible dates a year. And if you have even dates for, I don't know, 30 years, 50 years, it's still much, much, much less than 1 million elements, right?
Yeah, and so what we did here is like, after we started understanding our data and looking at it and seeing where the costs were, like we said, like, what can we, do here with pooling? And we saw like, well, we have a lot of duplicate cities. We actually have a set of 6 of them that we load. So immediately we can get rid of, let's say, 1 million strings and just through pooling wind up with 6. There's a tremendous savings, right? We have start date and end date. We have 1 million of each of those, right? And there's only 364 that we wind up loading for 2023. So we go from 1 million to 364, right? And then, as it turns out, session types, which Rustam talked about before with the CSV data, we've got, let's say, talks, workshops, lightning talks, right? So it's a combination of either anywhere from 1, 2, or 3, and then the combination of those. And you can see, like, in total, you wind up with 7 instances. Now, what's interesting is when you use the Eclipse Collections immutable set, you wind up with named classes for each of the sizes. So it actually tells you more about the distribution of your data. So we could actually see, and I refer to this as a tracer bullet. It's like I can see what's out there as I'm shooting my sets into the heap, what they actually look like and where they land, and see, like, I've got 375,000 plus singleton sets, 541,000 doubleton, and 82,000 tripleton, right? And those then reduce down to those. So yeah, so now we can talk a bit about rows versus columns and something to think about in this space. So
5-minute warning.
What? Yes, 5-minute
We have
warning.
5-minute warning.
So row-based structures, really, the benefit you get is, like, you can get custom tuning ability. You can actually really, let's say, try and compress down the data in your row. But you've got limits with that. You do have, also the ability to do custom pooling, which is what we did after the fact. And we're going to show a little bit of what we can do in terms of achieving more with rows to squeeze even more memory. But some of the challenges that you get is, like, you get this object header cost, right? So for every row, I got like an object header. We're going to talk a little bit about what Java is going to do eventually to help us in this space, right? You also have object alignment costs to think about, right? The way objects get this 8-byte alignment. So whatever you can fit into 8 bytes, if you don't fit 8 bytes though, you fit 4, it's still going to cost you 8. And you got to consider that. And there's a great article from Alexei Shipalev on object alignment and how that works. With column-based structures, you only get an object header cost per column, so a lot less columns. Let's say 10 columns versus a million rows, right? You get great compression and performance, especially if you've got primitive types. Things can maybe just be loaded directly in from a second-level cache into, to the processor and, get good cache locality. And then you are limited, though, in terms of, like, tuning to the available types. So data frame EC only has a long value type for integral values. It doesn't have short, int, or byte. So, that's a place where it could actually give you more savings. But let's go look at fine-tuning memory and Conference Explorer and what we did. So through some, just manual, what can I do to squeeze memory here? You can see and we only did it for the one column. We could have done it for all of the first 4, because this was really making changes in the conference record, changing the types. And what we did was we took what were 4 int fields initially, and we made one of the int fields byte, because, like, the number of tracks is always typically going to be less than 10, right? In a byte, I can fit 128, right? And then the int value is, like, I don't really need 2 billion for, like, number of speakers, number of sessions, and cost, right? A nice value is, let's say, short, it's much smaller. Hopefully you don't, hit the max size for the cost, but you're definitely not going to hit the max size for speakers and sessions, right? So what this gave us the ability to shrink a 16 bytes down to 7. And then we did this really gnarly trick of, like, hey, let's get rid of an object reference, and that'll save us 4 million extra bytes potentially if we can get the object alignment working out right. So we combine the 2 dates into this pair object. It's called the twin, because twin, same type. And basically we were able to reduce the reference cost, and this is that kind of funny date math, right? Now we had the combination of, like, from and to, but since 2 is always greater than from, you wind up with, like, at max, like, 66,000, and that's still a lot less than a million. So even if I have to create 66,000 of these at 24 bytes, right, the million times 4 is going to be more than that, right? So we got a savings from there. And what you can see is we effectively got the Eclipse Collections immutable list row-based approach to be a little more than 10 megs less memory than the data frame EC, where we didn't have to really do anything, right? So that's kind of explaining what happened here. So now let's turn the volume up to 11, so to speak, and talk about, like, we wanted to see what if we, turn the volume up, well, actually to 25, right, where we went from 1 million to 25 million. And we still have that manual tuning for just the Eclipse Collections column. But what we added here is we wanted to remind you on the file size, right? So you can actually compare, like, this is the file size that when we generated the 25 million objects, it took 2.1, 9 gig. And you can see in comparison, how much does it require in memory, right? Now, as it turns out, when we actually turned it up to 25 million and I tried to run our code, it exploded, right? We ran out of memory. And it turns out because we hadn't tuned this at all, like, we're using Jackson CSV, and we're using this mapping iterator read all method. And read all, what it does is it creates basically a list of maps. So we wound up creating 25 million maps, right? And maybe they were probably just JDK hash maps. So it's like it blew out the memory space. And what you need to do is like, well, in order to scale using Jackson CSV, we use the iterator directly. So we're creating one row at a time and then turning that into the conference row. So, not creating maps and then turning maps into conferences, right? So, and this was much better. But you can see like the manual savings here, though, is adding up. When you talk about 25 million rows, you can see like, oh, look, we're saving now over 300 meg compared to like data frame EC. So that manual tuning is starting to pay off, right? So we go to the next slide. We could talk a little bit about what's going to happen with Java. So
yeah, so we talked about quite a bit about actually how we can fine tune, and we can do it by knowing our data or using the right data structure for that. But there is also things happening in Java world that will bring the size of the memory footprint down a bit. There are a few projects that are working in different directions. I mean, they're doing different things, but all in all, at the end, most of them, at least two of them for sure, and the third one kind of, will influence the value of the memory footprint. So Project Lilliput works with techniques to downsize the Java object headers in general in the hotspot JVM from 128 bits to 64 bits or less. Project Valhalla will also have this thing called value objects. And if you want to read more about that, there are links to both descriptions of the project, but also to, in this case, a blog post by Brian Gutz, where he explains how this works. And it's kind of the interesting quote to take from here. It says, like primitives, the value set of an inline class in the set of instances of that class, not object references. And also Project Amber, which is not exactly memory related, but still will kind of influence it and also help to think about data-oriented programming and approach to that in Java. You can also read about that, and also you can read this article by Brian as well, which is a really, really interesting kind of insight of data-oriented programming in Java. So in summary, well, what we can say? Well, we can say that data-oriented programming in Java is actually possible. You don't need to go for another framework, language, whatever. You can do it. It's feasible, it's flexible, and it's actually fun. It can be fun with all this fine-tuning and small things that you can do and see your memory footprint kind of go down, and you can do all these fun things with you in your favorite language, right? Understanding and measuring your data is the most important key that will be there no matter what you choose, no matter what framework, language, whatever you will go for. It will be a very important part of it. You should use tools to measure that. You should consider using pooling to get a lot of memory benefits, especially if you have repeating values and values that are not absolutely 100% unique. Object compression is also a possible using smaller primitive types instead of fixed number ranges and stuff like that. With fixed number ranges. Yeah, so we need to think about also column-based approach versus domain-oriented or object-oriented approach to the structure. So when we do column-based, you should try to stick to primitives. Primitive will generate a lot of memory savings. You should think about providing support for smaller integral types that can add to the memory savings. When it comes to domain-oriented approach, we should think about how it can be tuned manually, because here you need to know your data, you need to know how it's put together, you need to know where you can cut things. And it's one of the most important things, one of the kind of the most low-hanging fruits probably is to convert things into immutable data structures after you're done playing around with it, doing something with it. Put it into immutable data structures and leave them there, because it will give you a better memory footprint. all the code, the presentation, and even more slides. As you can see, there is an appendices, and there are several more slides that you can see there. All of that is on that GitHub link over there as an open repository. You can also scan the QR code to get the link from that. And with this, unless you have anything to add, Donald, I want to go to the title page and say that you're more than welcome to ping us online. So this is us on Twitter. We'll be happy to discuss anything related to that or anything related to Java. Ping us. Thank you very much. Thank you for being here. Thank you for joining us. Thank you for having us.
Thank you.